We have seen how to calculate the electric field strength in between two parallel plates if we know the distance between plates and the voltage applied to the plates. It's a simple formula. All you need is to take the voltage and divide by the distance. Now, following up on this example, I shall now try and calculate the force that would act on an electron that is in between these two plates. So let's say I have the two plates. Now we'll continue with the previous assumption that the plates are quite long compared to the distance in between, so that the field inside most of the plate is uniform. Right, as I've mentioned, the plates close to the two edges are curved and not uniform anymore. So if I shall continue to use the same values as before for distance between plates of 1 centimeter, voltage between plates of 1.5 volts, and this time suppose that I have an electron, a tiny particle of electron. I'll call it E. So I use E also to represent the charge of this electron. And I'll just write it down here. The charge of an electron is very small. It's just 1.6 times 10 to the power of minus 19 of a coulomb. Very small number. So I want to calculate the force on this electron. Okay, so that would be, let's see, okay, let me just say positive charges on the top plate as before, and negative charges on the lower plate. So the positive charges would attract the electron, since an electron is negative. So the electron would experience an upward force. I'll call that F. Okay. Now, from calculation in the previous session, we know we have already found the electric field. Just write it out here again. It's the voltage divided by the spacing between plates. So that would be V. V would be this voltage of 1.5, and D, the spacing of 1 centimeter. So we have already calculated that it is 150 volts per meter. Now, to calculate the force, we would use the definition of electric field, force over charge. So electric field is equal to force over charge, right? So therefore, force is equal to charge times electric field. And charge in this case is E, is this value. So that's just E times electric field. If I work that out, that's 1.6 times 10 to the power of minus 19 from here times the electric field of 150 from there. So the answer is 2.4 times 10 to the minus 17 Newton. A tiny force. Now what I like to do here, what I like to do next is to compare this with the gravitational force on the electron. Okay, and let's see how that compares. The gravitational force is given by the weights, of course. The weight is mg, mass, times acceleration due to gravity. What's the mass of an electron? Okay, let me write this down. The mass of an electron, I'll write it out here. M is usually given the symbol M with a subscript E. Is 9.1 times 10 to the minus 31 of kilogram. That's an extremely small value, very, very small mass. If I want to calculate the weight of this electron, I would use this formula. So let me substitute this into the M. 9.1 times 10 to the minus 31 times G, which is 9.81. And the answer is 8.93 times 10 to the power of minus 30 Newton. Let's compare the weight of the electron with the weight from the electric field, from the electrical forces from these parallel plates. The electrical force is of the order of 10 to the power minus 17. The gravitational force is of the order of 10 to the power of minus 30, or maybe minus 29, if you take that to be about 10. So if you compare these two, 10 to the power of minus 30, 10 to the power of minus 70, the ratio is, you can just subtract the power. 30 minus 17 is 13. So 10 to the power of 13. Okay, the electric force is 10 to the power of 13 times more than the weight. So how could I write this? Now I'll write it here. So this if I compare the two, you'll find that the electrical force, which I call F, the electrical force, is about 10 to the power of 13 times of the weight. So the electrical force is much bigger than the weight, and all this just with a simple 1.5 volt battery that we can buy from the shops, and just two simple piece of metal plate. You can even use aluminum foil at a spacing of 1 centimeter apart. So for using for voltages and distances that we are familiar with, that people are familiar with, right? For these typical voltages and distances, the kind of force that we can get on an electron, right, would always be much bigger than the weight of the electron. So if, for example, in the next session, when I have to calculate when I want to calculate the motion of an electron in an electric field, it would almost always be okay, or unless we're talking about forces in atoms and not even that, it would usually be okay to just ignore the force of gravity when we do calculations with such problems.